Why hello, you people from Earth and outer space. It's I, Alexander from the universe. In this episode of Let's Rust, we'll cover some of Rust's primitives, the numeric types. There are various different types of primitives in Rust. Primitives referring to the different most basic types any binding can take on, such as the I32, which we talked about in previous episodes. Let's go ahead and define ourselves a nice variable binding. Let x equals say 8. Now this is automatically going to take on the type I32, which we can explicitly tell the compiler to use using a colon after the binding name. Tell it to use this type as an I32, like so. Now this is going to be perfectly valid if we're to use cargo to run this project. Type in cargo, run, and it's going to say, hey, there's an unused variable here. And that would make sense considering we're never using the x binding. But we also notice that the compiler ain't complaining about our usage on I32 being equal to 8. But there are more types a binding can take on. In fact, there are 4 different types of integers any binding can take on. Now we've only used the I32 so far, but there's also an 8-bit version. There's a 16-bit version, a 32-bit version, and a 64-bit version. The number after the I decides on how many bits we wish to store this binding inside. Meaning that depending on how big we need our variable binding to be, we can choose a different bit size for it. But these are the integers. And an integer that you're probably already used to from math class is a whole number that can be either positive or negative, but we cannot have them contain decimal points. What if we wanted a number such as 8.2? Now the compiler, since we're explicitly telling it that this variable binding is of type I64, it's going to generate an error for us. It's expecting an I64, but it finds a floating point variable. Now a floating point variable is what is known in most programming languages as a float, and it's also known as a float in Rust. A float being short for a floating point number. If we wanted to change this into a float, we could type in f followed by the number of bits we wish to store this inside. And as for floats, there are only 2 different bit sizes it can take on, either 32 or 64. Let's define it inside an f32, because we don't require 64 bits of data to store 8.2. That would be really silly of us. So we go ahead and run this. It's going to be like unused variable x. Hurrah, it works. But considering Rust has type inference, it would actually be quite weird typing in F32 when finding a variable binding. So let's go ahead and remove this, and this is going to work just fine. If we run this, it's going to say unused variable x. Wonderful. So it's working. It is worth to notice, however, that Rust's type inference automatically makes it of type F64 rather than F32. Now floats are all nice, but there's another type of integer that you may use when programming your program. Let's say we have a money binding, and it's equal to 32. Now this is by default going to be a regular integer, but there are times when the value of money is so big that an integer cannot store it. Now on times like these, we use the unsigned integers, which is a u followed by any bit size that we can think of, either 8, 16, 32, or 64. Let's create a U8. When we run this, it's going to be like, hey, unused variable money. Now the thing with unsigned integers is that they cannot store values below 0. So 0 is the minimum value for an unsigned integer. If we were to type in, say, -8, run this, we're going to get unary negation of unsigned integer. Unsigned integers, although they cannot access any number below 0, they can take on double the size of a normal integer. Since rather than using both negative and positive numbers, it only uses positive numbers, meaning that it has the lower half of all the bits it's stored inside to put into positive numbers rather than having to put them as negative numbers like the regular integer does. Now it doesn't matter what type a variable binding has in order for us to print it out, so we could just as well print out a U8 as we could an I32. we're gonna do this, tap it out, and we're gonna add, we have in dollars. And we're gonna have to change this because this is gonna generate us an error. So we have $8. It's gonna say we have $8. Isn't that beautiful? Now, there are two more types that you should just put in memory because we don't have the required knowledge to use them as of now. There's the I size and there is the U size. Now these are the variable size types. Variable size types, I size and U size, have a size dependent on machine architecture, but they're always of sufficient size to be set to the size of any collection. So for an example, you know for a fact that a U size is always going to be of sufficient size to be set to the size of any array, any type of collection. Now if you don't know what a collection is, you're obviously not going to be able to use it, but put this inside your memory and think of them as having a good long size that you can use for a whole lot of things. U size and I size are really useful, but you can think of them as decoration for now. If you wanted to, you could print this out like we have all other variable bindings, and it's going to say we have $8. But whenever you want to have a regular number, go and rather use the I32 or the U32 depending on what kind of calculations the specific numeric type requires. Now let's say we want to define two bindings, an X and a Y coordinate, and we want them to have different types. Because by default, because this is going to be two integers that we're defining, we're going to need to change this into X and Y, and we'll assume there's a battleship over at these coordinates, X and Y. Run this, it's going to say there's a battleship over at 3243. But what if you wanted one of these bindings for some reason to be of type I8 and the other one to be of type U8? And we could type a colon after these two names, make a new parenthesis, and would say U8, I8. So the X variable binding is going to have the type of U8 and the Y binding is going to have the type of I8. If we run this now, it's going to be perfectly valid. Just that the different bindings have different types inside this pattern, as we call it. And that makes a rather simple explanation of the different numeric types there are in Rust. Use different types as much as you can. If it's possible to use an unsigned integer, go for it. If you require an integer, then use an integer. If you need decimal point values, that it's worth notice that the floating point numbers correspond to the industry standard IEEE 754 single double precision numbers. A link will be in the description below if you're one of those students who really like to read up on your work and get really good before everybody else. There's some really good information there. Why goodbye, people from Earth and outer space. Feel free to leave a comment stating something utterly hilarious or perhaps even a like. Until next time.